Well, thank you everyone for coming today to the webinar. Today we have Katsuki Aoki from Yukawa Institute for Theoretical Physics in Tokyo, in Japan. Katsuki, let me check my notes just not to say anything wrong. Katsuki did his PhD finishing in 2017 in Waseda University, where he also stayed for a postdoc for a couple of years there. And now since 2019, he's a postdoc in the Yukawa Institute for Theoretical Physics in Tokyo. And his research has been focused mostly on cosmological aspects of modified theories of gravity, like by gravity or massive gravity. And today we have him here, and we are very happy to have him here to talk about the recent work of him, titled Gravitational Positivity Bounds, that appeared just this summer on the archive. And just before starting, let me remind you that if you have any question, you can ask them at the end of the talk. And if your mic is not working for whatever reason, or you're just shy to speak in public, you can use the chat. I will be monitoring the chat and I will read the questions at the end of the talk, okay? So, well, Katsuki, it's your time.
Okay, thank you very much. And thank you very much for inviting me this nice webinar. And I'm Katsuki Aoki, and the title of this talk is about gravitational positivity bounds, and based on this paper. And the collaborators are Junsei and Shinichi, and all of us are postdoc now. Okay, let me start. And I think some of you already know what's a positivity bound, but some of you do not. So before any details, let me briefly explain what are positivity bounds and why this kind of bound can be obtained. And I think almost everyone believes there is some UV theory in the UV regime, so quantum gravity. But maybe it's string theory or other theories. But this theory is defined in the UV regime. But so in practice, if you want to discuss some low energy phenomena, maybe UV theory is not so useful because there are many ways to predict the low energy phenomena based on the UV theory. So in practice, the EFT, effective field theory, is more useful. And observation determine or constrain the parameter of EFTs. And there might be some hidden relations between EFT and UV theory, and positivity bounds are actually one of them. So this provides some non-trivial relation or some non-trivial requirement for EFT from the UV theory. So this is very, very naive argument, but I think you can understand why this kind of relation exists from this naive argument.
Yeah, sorry, Katsuki, I just mute everyone in the talk, including you. Sorry for this. Can you mute you and...
Oh, okay, thank you. Can you hear me now?
Yes, now it works. Sorry
okay.
about this.
No problem. Okay, so let's consider the UV theory and consider the scattering problem of the light particles. So external states are just light particles. And this is UV theory, so we have some hidden heavy particle, and this scattering is caused by this exchange of this heavy particle. And this is a picture of UV theory. But if you go IR regime, then this heavy particle is effectively non-dynamical. That means this scattering is essentially caused by just local process, some 4-point interaction of the EFT. And so this amplitude is proportional to the 4-point function, a 4-point interaction of EFT. So it seems that the sign of this coefficient is arbitrary. It can be either positive or negative from the EFT point of view. But if you back to the UV theory, we have a heavy state, and we have coupling constant. So that means the amplitude of this amplitude is proportional to g squared times propagator of this heavy state. And this is, of course, positive quantity because there is a square. And if we suppose this heavy state is neither ghost nor tachyon, I mean this UV theory is a standard UV theory, then the sign of propagator is also fixed. That means that from the point of view of UV theory, the amplitude of this process must be positive. And by definition, in IR regime, two results give the same result, meaning that this sign of the EFT must be positive. this is a very rough argument of the positivity bound. And we get the constraint on the 4-point interaction of EFT from the UV theory. And there are many motivations to discuss this kind of bound. And I think the one with the most practical motivation to discuss this kind of bound is to excluding some apparently consistent theories. So if we look at the universe, so there are many unknowns like dark energy, dark matter, and inflations. And also there are many models to explain them. So someone says that the inflation causes the inflation of the number of theories. So there are many theories. And let's consider two simple models, DVI and the so-called anti-DVI model. The difference is the sign of this part. And this kind of model is cosmologically interesting in the context of, for example, DVI inflation. On the other hand, this kind of model would be interesting from the astrophysical point of view because this kind of model can have a successful screening mechanism. I mean that in IR, phi scalar field can carry the force, but if you go to the small scale, then this force can be suppressed by this kind of nonlinear interaction. So that means that gravity can be modified at large distances, but it recovers GR at short distance. So it's interesting. But the positivity bands are derived under the following 4 actions of the amplitude. So first assumption is a unitarity, and second one is Lorentz invariance, and third one is a causality, and fourth one is a locality. And these are almost everyone believes that standard theory has this kind of property. And I think you know what is unitarity and Lorentz invariance, but let me explain the analyticity and boundedness. So causality concludes the analyticity of the amplitude, and this assumption is more practically important to derive the positivity bound. And analyticity means the scattering amplitude is essentially regular function, except some particles are created. But anyway, analyticity means a function. Amplitude is a regular function. And the boundedness is derived under the locality assumption of the theory, and this says that the function is bounded by a power of energy. So there is no exponential growth. The growth is just a polynomial. This is a boundedness assumption, and it's obtained by locality assumption. And if you assume that these 4 properties of the amplitude, then we can derive the positivity bound. So it's a very strong statement. And this bound excludes this kind of model. So this sign must be excluded. So this is very strong statement. And even if this model is interesting, we should exclude this kind of model if you believe that this kind of property. This is practical motivation. But I think more interesting motivation is this bound can be used to reveal UV physics. Because in the standard maybe particle physics, maybe these 4 properties are satisfied. But if you consider gravity, then maybe some of the assumption would be violated, like a non-local theory of a Hodge-Lifshitz type quantum gravity. So in this sense, if we observe some violation, then this implies there exists some non-trivial or some exotic quantum gravity in the nature. So this will be interesting. And also the final motivation is this kind of argument can be used to prove some conjectures. For example, this paper discusses weak gravity conjecture could be proved if we use a positivity bound. And if this is correct, then this kind of conjecture can be upgraded to theorems. Then we can get a more strong statement on EFTs. So from any motivations, maybe positivity bounds are very interesting and very useful. But these arguments are based on non-gravitational theories. And the story is not so simple when gravity is included. So this is the main topic of this talk. So this is the contents. So first of all, I would like to briefly review the standard derivation of the positivity bound without gravity. Okay, let me start. So in this talk, we consider the scattering problem. So we consider 2-2 scattering of the right particles. So there are 2 in particles and 2 out particles. And for simplicity, in this talk, I only focus on the scalar scattering. So external particles are just the same real scalars with a mass m. And so this process is determined by the scattering amplitude. And we suppose the Lorentz invariance. And Lorentz invariance means there is conservation law. And this Lorentz invariance concludes that the scattering amplitude is given by the function of two Lorentz invariant variables. In non-relativistic system, the amplitude is a function of center of mass energy and scattering angle. But S and T are Lorentz invariant counterpart of these two variables. And S represents the center of mass energy square, and T is momentum transfer. And essentially, T is a scattering angle related by this kind of relation. And it is also useful to introduce additional variable U, and conservation law concludes this kind of relation. So only independent variables are just S and T. And these three variables are called Mandelstam variables. And these variables represent the intermediate momenta of these three important processes called S-channel, T-channel, and U-channel process. S-channel process means some two in particles are annihilated and then created, and this kind of process. And T-channel is a kind of standard scattering. So the particle emits some particle, and this particle carries the force, and then the particle is scattered. And U-channel is also another possible process. And in terms of these variables, the physical region of the scattering amplitude is given by this one, because energy must be greater than rest of mass energy. Then we have a lower bound of energy, and the angle theta must be real, and this gives a constraint on T. And from this constraint, we have also the bound on U. This is a physical region. And in terms of these variables, T goes to zero limit is called forward scattering limit. This corresponds to theta to zero limit. So essentially, there is nothing. So just a particle goes straight. And S is related to the energy of the amplitude, this process. So if we take infinity of S, then this corresponds to the high energy limit of the scattering. And also the scattering amplitude has a nice property called crossing symmetry. So this means if you consider S channel, and if you rotate this channel, then and relabel the momenta, you find a T channel. That means that there is some symmetry between the T and S channel, and this gives a symmetry of the function. So this scattering amplitude is invariant under the displacement of the SUT variables. And the most important property is for the positivity bound is the optical theorem. So unitarity concludes the optical theorem, and this means the imaginary part of the amplitude in the forward limit is given by total cross-section, and cross-section is positive quantity by definition. So that means the imaginary part of the amplitude in the forward limit is positive. So this is a consequence of the optical theorem. And so far, we only consider the physical region, but in the discussion of the positivity bound, we extend this function into the full complex plane by analytic continuation. So we not only consider physical region, but also consider unphysical regions, and sometimes S can be complex and T can be complex. So this is just a complex function of the complex ST variables. And then let's consider the let's explain the analytic structure of the amplitude, analyticity. So let's consider amplitude as a complex function of S for fixed T. So let's fix just T. So T is some constant, and the variable is just S. So this is a complex S-plane, and represents the analytic structure of the amplitude. And the causality concludes that this amplitude of f of S has singularities associated with SU channels, and the other part are regular. means that if you consider if energy is same as mass, then some particle can be created, and this gives some kind of resonance, and this gives a pole on the scattering amplitude. So there is a singularity here corresponding to the particle exchange of the S channel. And also, if the energy exceeds some energy of the sum of two particles, then some multi-particle state can be created. And this gives a branch cut of the amplitude. So we are considering the complex function. So the function is not single valid function. And in this figure, the branch cut means this part. So there is discontinuity between the two parts. And we only focus on the first Riemann seat. Then the causality concludes that there is no other singularities except pole and branch cut. And this is a pole associated with S-channel exchange. But in general, we also have a U-channel and T-channels. But we are fixing T, so there is no T-channel in this complex plane. But we have a poles and branch cut from the U-channels. So in general, the analytic structure of the amplitude in the complex X plane is given by has two poles associated with the S-channel exchange and U-channel exchange, and branch cut correspond to the loop diagram. And if we have several exchanging particles, the number of poles increase. So if you have for example, scalar exchange, we have a pole here. And if we have also the graviton, then we also have a pole at S equal to 0. So this is the analyticity of the amplitude. And if you understand this kind of property, or if you accept this kind of property, then it's not so difficult to understand to derive the positivity bounds. So the analysis is essentially just a complex analysis. So let's use the Cauchy integral formula. That means some complex function can be given by an integral of the function. So this is a Cauchy integral formula, and we have an identity. And we know the analytic structure of the amplitude. That means we can deform the contour. And somehow we can get this kind of expression after deforming contour. So that means the left-hand side is just amplitude. But the right-hand side is given by integral of the imaginary part of the amplitude. And this is just a local quantity. That means that if we suppose a small s, this is a amplitude at IR. I mean, this quantity can be calculated based on EFT, because we only need the low energy information to compute the left-hand side. On the other hand, right-hand side is given by integral, and the integral runs from the low energy part to infinity. That means that to compute this integral, we need full information of the theory. So in general, we cannot compute this kind of quantity. But we have an optical theorem. Optical theorem concludes the imaginary part is positive. That means the integrand of this integral is positive. That concludes that the integral is of course positive. That means the right-hand side is positive because of the optical theorem. And the left-hand side is computed by EFT. That means that we can compute this quantity based on your EFT. And we know that this relation and the right-hand side is positive quantity because of unitarity. That means the left-hand side must be positive. That gives a constraint on EFT parameters. So this is very basic idea of the positivity bound. So how to derive the positivity bound. Then let's explain some detail of the bounds. So first, we need to know the asymptotic behavior of the amplitude to deform the contour, because we want to ignore the contribution from the integral along infinity. And there are famous and very nice bound derived by Floizard. And this is very nice because this bound is derived under very just a unitarity and causality and locality. And this bound is derived for a gapped system. So we can use this bound without assuming any UV complete UV theory. And this says that f grows at most power of S2. So that means that if we take this kind of factor, if we add this kind of factor, then the integral along the infinity can be ignored. So this is just technical point. But anyways, we can use this kind of Cauchy integral formula. And thanks to this kind of closed-out bound, we can ignore the contribution from the infinity. Then using the Cauchy integral formula, let's deform the contour. So we first consider some point, and the amplitude at this point can be computed by the integral along this contour by using this expression. And this is the identity. And we know the analytic structures. We have poles and branch cut. So this contour can be deformed into this kind of contour. So that means we have an integral along the branch cut, and then the integral along the infinity, and along the right branch cut and the infinity. But thanks to the closed-out bound, we can ignore the contribution from this integral. And also we have a poles, so we need to subtract the pole contribution. So we need to add this kind of contour. But anyways, we can get this kind of expression. And this is called so-called twice subtracted dispersion relation. And this relation represents the analytic structure explicitly. I mean, the scattering amplitude is given by sum of the poles and some integral along the branch cut and some polynomial terms. And using the Cauchy integral formula, we can derive this kind of relation. And this is still a little bit complicated, so let's rewrite it in a more simple expression. So the left-hand side of the dispersion relation is amplitude at low energy. And at low energy, we may have a S-channel diagram, T-channel diagram, U-channel diagram, and also 4-point sum diagram, and maybe loop diagrams. On the other hand, right-hand side is given by sum of S and U-channel poles and integral of imaginary part and some polynomial terms. And these terms are irrelevant if we take derivatives, because this is just polynomial. That means that if we take, for example, 2 derivative of S with respect to S, then this kind of polynomial term disappears. So these are irrelevant. Then let's define the pole subtracted amplitude, meaning that we just subtract the pole from the original scattering amplitude. And this, by definition, poles are subtracted, so this quantity is finite. So this amplitude is given by some finite quantity plus 4-point interaction plus loops. And we have in the left-hand side, we have a S, T, and U channel. And the right-hand side, we have a S and U channel. And these 2 channels are canceled if we use this kind of pole subtracted amplitude. That means if we use this pole subtracted amplitude, the dispersion relation is given by this form. So that means the left-hand side is a regular quantity, regularized amplitude at IR, and we have an integral of imaginary part, and also the T-channel contribution. Because T-channel is not canceled, because right-hand side has only S and U channels. But left-hand side, we have T-channel as well. So S and U are canceled, but T still remains. So we have a T-channel contribution here. Anyway, we can derive this kind of expression. And left-hand side is a regular part of the amplitude, and evaluated at IR. And sorry, I didn't explain, but this 2n means the derivative with 2n derivative with respect to essentially S. So this is the derivative of this one. And the right-hand side is the integral of imaginary part. And also we have another term, T-channel. But it is known that the T-channel is proportional to S to J, and J represents the spin of the exchanging particle. And if we that means the power is 0. and we are taking a derivative, that means that this term also disappears. That means that if there is no right spin J exchange, if the J spin higher than 2 spin 2 exchange, then we can ignore this part. And then we get just the imaginary part of the integral of the imaginary part. And we can use the optical theorem. So after taking the forward limit, then the integrand is positive. That means the integral must be positive. So right-hand side is positive if we take a forward limit. Then we get the positivity bound. So this left-hand side must be positive for all n. And roughly speaking, this means the regular part of the amplitude at IR must be given by this kind of form. So some positive quantity times s squared plus positive quantity times s4 and so on. And there are no odd power of s because there is a crossing symmetry. So we only have a s2, s4, even power of the s. But anyway, we can derive this kind of bound by assuming the full assumption on the amplitude. And this means that the regular part of amplitude must be positive quantity like this. And if you apply this bound to this model, then you find this quantity must be positive. And also some paper discuss an extension of this kind of bound. So this gives a bound on the S dependence of the amplitude, but we can also get the T dependence of the amplitude because optical theorem also concludes the derivative of imaginary part is also positive. And by using this inequality, we can also get a little bit complicated, but anyway, we can get a constraint on the T derivative. And also another extension is called improved positivity bound. So optical idea is simple. So optical theorem concludes that imaginary part is given by sum of the positive quantity. That means that even if we subtract some of this intermediate state, we still have a positive quantity because this is sum of the positive quantity. That means that we can subtract some norm part of the imaginary state, intermediate states. And maybe I can skip this part, but anyways, for example, if we consider some EFT with a cutoff around the EFT, that means that we can compute the quantity below this scale. That means that we can compute the imaginary part up to this scale. Then the original imaginary part integral runs from 4m squared to infinity, but it can be divided into the low energy part plus UV part. And because we know EFT cutoff is this quantity, meaning that we can compute this integral. So let's subtract this quantity. I mean, let's move this quantity to the left-hand side. But the right-hand side, we still have a integral of the imaginary part, and this is positive because of the optical theorem. That means we have this bound. And this is definitely positive quantity, meaning that this bound, positivity bound are improved. So this is called improved positivity bound. Anyway, this is a review of the standard positivity bound without gravity. And if in the absence of gravity, there is no problem to derive this kind of bounds. But if you turn on the gravity, there are actually many problems. So first problem is analyticity. So graviton must be massless particle. And massless particle means that even if the energy is smaller than 4m squared, m is a scalar, mass of scalar, we have a loop diagram of the graviton. And this gives a branch cut. And in the previous example, we have a branch cut in the left part and right part corresponding to the U channel loop contributions and S channel. And two branch cut are separated. But if you consider massless particle, two branch cut connected, that means we cannot easily deform the contour. But fortunately, gravity is very weak. That means, if we suppose that gravity is usually completed below the scale of Planck scale, then probably we can ignore graviton loops up to the usual completion of the gravity, because this scale is smaller than Planck scale, and graviton loops are suppressed by Planck scales. So if we support this kind of usual completion, probably we can ignore the graviton loops. In that sense, maybe we can assume the standard analytic property even if we turn on the gravity. It's a problem, but maybe resolved by assuming that this kind of, if you ignore graviton loops. But still, we have another problem. This is boundedness problem. So the Floyd-out bound is derived for the gapped system. I mean the system without massless particle, but graviton is massless particle. So we cannot derive the Floyd-out bound. And if the gravity does not couple to matter field, then we may derive such a bound for such a system, but the gravity is a universal force, so we cannot ignore gravity. So essentially, we cannot derive this Floyd-out bound. So this is also a problem. However, we may suppose a similar boundedness property like this. So the F divided by S square is 0 for negative t. And this is actually just assumption. But if we look at the string theory, this kind of property is satisfied thanks to so-called Regge behavior. The Regge behavior means a power is a function of t. And this kind of behavior is caused by the higher spin states of the string theory. But anyways, string theory predicts this kind of property of the amplitude. And this function is negative for negative t. That means the power is smaller, slightly smaller than 2 for small t. Since this kind of bounded, like a Floyd-out kind of bound is satisfied even for gravity system. So I think there is no proof of this kind of boundedness property for gravitational system, but it will be reasonable to assume that this kind of boundedness property. So in some sense, this kind of problem is also resolved. But still, we have a problem. Under the assumption of the analyticity of the boundedness, we can still deform the contour, and we can still derive the subtracted dispersion relations for negative t. So we can get this kind of expression even for gravity, even for gravitational system, if you suppose the analyticity and boundedness. But difference is the existence of the t-channel pole of the graviton. So here B is a pole subtracted amplitude, and in general, the amplitude contains exchanging scalar exchange diagrams and also graviton exchange diagrams. And we subtract the all pole contribution from the left-hand side. Then we get the pole subtracted amplitude, but we subtract the graviton. That means there is a graviton t-channel here. And this is actually an essential problem. Because here, left-hand side is a regular part, regular quantity. But the right-hand side is given by sum of the integral plus the t-channel contribution. And in the previous case, power is 0 because of the scalar exchange. But we are considering the graviton exchange. That means the power is 2 here. And so even if we take 2 derivatives, we still have some remaining contribution from the t-channel. And this is t-channel, and graviton is massless. That means that this t-channel is proportional to 1 over t. But we want to use optical theorem. So we want to take a forward limit. But clearly, this quantity diverges if you take a forward limit. That means the divergence quantity exists here. So this expression means that there is divergence. That means we cannot say anything on this bound for n equals to 1. Still, we can derive the bound for large n, but the n equal 1 bound is the most important for phenomenology. For example, if you consider this model, then actually this bound is obtained from the n equal 1 bound. But if you turn on the gravity, this bound cannot be believed. So we cannot get this kind of very interesting constraint on the EFT. And we want to try to resolve this kind of problem. So these are related arguments, but time is limited, so let's skip this part. So okay, let's back to this dispersion relation. So as I said, left-hand side is a regularized quantity. That means that this is definitely finite, even if you take a forward scattering limit. On the right-hand side, we have a divergent quantity because of graviton T channel. So we have divergence. But left-hand side is finite quantity, meaning that there must be infinity minus infinity, giving rise to some finite quantity after the cancellation of infinity. So the finiteness of the right-hand side concludes that this integral must diverge if we take a forward scattering limit. So this quantity must diverge. But we know the boundedness property. The boundedness property concludes that this quantity is finite for negative t. So integrand is finite, even if we take a forward scattering limit. So that means that explains the origin of infinity. So origin of infinity of this integral is this infinity. So the divergence of the integral comes from the infinity of the domain of the integral. That means the right-hand side is given by sum of the integral plus t channel, and this integral can be divided into some low energy part plus some UV part, and this UV part cancels the t channel contribution and gives a finite quantity. So we can at least understand this kind of property from this dispersion relation. And this is indeed the case in the case of superstring. So I'm not so familiar with the superstring theory, but anyway, the point is this kind of amplitude is predicted by superstring, and this amplitude is a kind of UV complete amplitude. That means that we can compute both of left-hand side and also right-hand side of the dispersion relation. And this amplitude has a pole associated with a graviton, and also the pole associated with the higher spin states of the so-called Regge state. And the left-hand side is the IR quantity, and these Regge states are heavy state. So in IR, we only have a graviton exchanges. So that means that left-hand side is given by sum of the graviton exchange diagrams. On the other hand, right-hand side is given by integral, and this integral is divided into low energy part plus high energy part. And this low energy part is a contribution from the graviton pole, and high energy part contribution from the higher spin pole contributions. And we have this identity. And left-hand side has 3 poles, and right-hand side contains poles associated with the graviton SU channels and also higher spin states. And this part and the graviton SU part of the IR part cancel. That means the graviton T channel must be same as the sum of the all higher spin state. And we can explicitly confirm this kind of relation. And I think this is well-known result. But this tells us that the graviton T channel is cancelled with the Regge state in the superstring theory. And these Regge states are UV degrees freedom of the theory. That means the T channel is cancelled with the UV part of the integral. Then we can easily understand what we need to derive the gravitational positivity bound. So additional requirement is the UV behavior of the amplitude, because we need to compute this quantity explicitly, and we need to confirm the cancellation explicitly. And in this talk, we just suppose the Regge behavior, because this would be the most natural UV behavior of the gravity, because this is predicted by superstring theory. Of course, maybe you can support another kind of behavior, then you may get another result. But anyway, we just support this kind of behavior. And maybe these are just technical, so let's skip.
Okay,
so
sorry,
anyway,
to interrupt you, but you have like 10 to 15 minutes left.
Okay. It's okay. So it's not so important. So what is important is we just suppose that this kind of UV asymptotic behavior of the amplitude. And if we suppose that this behavior, we can compute the integral. And assuming this amplitude behavior, this integral is given by the 1 over t term plus some finite quantity. And t channel is, of course, proportional to 1 over t. And from the finiteness of the left-hand side, these two parts must be canceled exactly. And we still have a finite quantity. This gives a finite modification or correction to the standard positivity argument. And this is a result. So we have a finite quantity in IR part is same as the sum of the integral of imaginary part plus some finite residual contribution after the cancellation of the infinity. So this expression has no 1 over t term, so we can take a forward scattering limit safely, and then we can again use the optical theorem to conclude the positiveness of this imaginary part. Then we find some bound on this IR quantity. So we obtain the manifestly finite expression even for the forward scattering limit. And one interesting result is that the unitarity concludes that negativity is allowed. That means if you consider superstring theory, then this function, this is a power of S, is linear in T in the string theory. And this is a derivative with respect to T, so that if this is linear, this quantity vanishes. So we only have this one. And this one is given by the imaginary part of the amplitude, so T derivative of the amplitude. And as I said, optical theorem concludes that this quantity must be positive. And also this quantity also positive to satisfy the boundedness property. And we have negative quantity here. That means the first term is actually positive definite quantity, but second term is negative definite quantity. So that means that in general, the sign is undetermined. So in general, in the presence of gravity, we cannot conclude the positiveness of the amplitude. So in some sense, the wrong sign is allowed because thanks to the unitarity. So actually, unitarity concludes the negative sign. But in practice, this negativity is highly suppressed. This is because these contributions are UV quantities, and this is suppressed by not only Planck, but also string scale, so alpha prime. So alpha prime determines the property of the Regge behavior, but in typical example, in the string theory, this is given by string scale -2. So this is suppressed by, highly suppressed. So that means this first term dominates over the second term. So in practice, we can ignore this highly suppressed quantity if you are interested in very low energy EFTs. For example, if you consider this kind of EFT, so we are at the gravity, and if you are interested in cosmology, then this cutoff of this EFT would be given by Planck times Hubble scale if you are interested in cosmology. This is a typical case for the cosmological studies. And if you are considering, for example, dark energy, then the Hubble is extremely small. So compared to the string scale, that means essentially we can ignore this term. So we can get this bound approximately. And even if you are interested in inflation, the current observation concludes the Hubble must be smaller than 10 to 14 GeV, but the expected scale of the string is 10 to 16 GeV. That means we can still ignore this kind of negative contribution, and we can also say the positiveness of this coefficient. So that means we can get a kind of approximate positivity bound. So regular part of the amplitude at IR is approximately given by positive quantity times S squared times positive quantity times S4 and so on. So in practical, we can use this kind of approximate positivity bound even for the gravitational EFTs. But this is one scenario, but I think more interesting scenario is as follows. So this is a typical scale, the expected scale of superstring, but we are not sure the true scale of quantum gravity. So observation must determine the true scale of quantum gravity. And what we found is that if the cutoff is comparable to the scale of quantum gravity, then the negativity is allowed. That means that if we find some observational signatures of the violation of the positivity, then this could be a signature of the quantum gravity. So this will be interesting scenario. Of course, we should discuss whether this is we should discuss degeneration of the observations. So maybe violation of positivity just means the theory is not given by such a EFT. But if we confirm somehow the violation of positivity, then we can say that we find quantum gravity. And these are some related arguments of the present work. For example, this paper also discussed the same kind of the argument. So they assume the Regge behavior in UV, and they also get almost same conclusion. So we can derive the positivity if the cutoff is smaller than this scale. But they do not explicitly show the cancellation of the T-channel. So they just argue that this kind of positivity may be satisfied if the cutoff is smaller than this scale. And this is completely different argument. They consider the purely low energy EFT argument, and also discuss negativity may be allowed in the gravitational system. But in this case, they conclude that positivity is satisfied if the lambda is smaller than this quantity and n is the cutoff of the EFT, because they discuss they consider purely EFT argument. But we are supposing the UV theory, then we can improve their argument. So our result is if the lambda is smaller than string scale, then we can use the positivity bound. But anyway, our results are consistent with their argument. And another discussion is made by this author. And their claim is that this graviton T-channel can be cancelled when we consider Katsuki compactification and the optical theorem. But for example, this paper actually, one of the main results of this paper is pointing out some subtleties of the paper. And maybe I shouldn't comment on this point, but anyways, some subtleties are argued in this paper on the analysis. So this is a derivation of the positivity bound in the presence of gravity. So let's use this result to some concrete models. So to derive the positivity bound, we need to support the unitarity, Lorentz invariance, analyticity, and Regge behavior. And if we are interested in low energy EFTs, lower than the quantum scale of the quantum gravity, then we can still use the standard positivity. And maybe
you have like about 5 minutes. So.
Oh, really? And it explicitly explains this model. So first, as an example, we consider this kind of model. So we have Einstein-Hilbert action and scalar field as non-minimal coupling to gravity. And these kind of interactions are discussed in the context of inflation. And our bound is actually gives a non-trivial constraint on these kind of non-trivial non-minimal couplings. And one interesting thing is that positivity bound gives a constraint on EFT cutoff. And these couplings are gravitational couplings, meaning that there is a Planck suppression. So amplitude is proportional to Planck times the cutoff m of this coupling. That means that naively, part of it concludes the cutoff is this quantity, so-called lambda 2. But positivity concludes the cutoff must be n. From the action, maybe it would be natural to suppose M is a cutoff because this is a higher dimensional operator, and this operator is suppressed by this quantity. But from the level of the amplitude, it seems the cutoff is given by this quantity, but the positivity provides a more strong constraint on the cutoff of this theory. And this is just a toy model. And in the paper, we discuss most general scalar-tensor EFTs and discuss the positivity argument on the EFT. And this paper discusses so perturbative field definition of the variables. We are interested in EFT, and EFT is invariant, or theory invariant, even if we take a field definition. So even if we change the variable, the theory is still same. And by using the change of variable up to dimension 11 operators, we can get the ghost-free theory. And at the dimension 12, we found the first ghost-free operator. And positivity bound gives a bound on this kind of ghost-free operator. And this is our bound. And these coefficient complicated expressions, but this is this gives a ghost-free coefficient of the ghost-free operator. So if this vanishes, then the theory is ghost-free. And due to the loop contributions, we have an additional contribution from the ghost-free operators. And this means that even if the theory is free from ghost, I mean the disk quantity is negative, not zero, then the disk inequality is satisfied. So in that sense, the ghost operators are expected from the quantum collection, but positivity do not exclude the ghost-free theory. So ghost-free theory is consistent with the positivity argument. And also, this is a final application on the phenomenological model. So if you suppose a scalar plays the role of dark energy, we have many constraints on the speed of gravitational wave and the graviton decay and so on. And if we consider ghost-free model, then from these constraints, the variable scalar tensor theory is given by this Lagrangian. So X is a kinetic term of scalar field. And if you consider positivity bound on this variable model, then we get this kind of bound. So this gives a bound on the X square term of the nonlinear kinetic term, and this is a non-minimal coupling term, X times this scale. And if we forget about gravity, so if we forget about this kind of non-minimal coupling, the bound is simply given by this quantity must be positive, and this is well-known result. And this is also well-known that this kind of positivity bound contradicts the success of kinetic screening. But we have an additional contribution from the non-minimum coupling. So even if this quantity is negative, then this kind of positivity bound can be satisfied. So we are not discussing the screening mechanism of in the presence of this kind of operator, but maybe the non-minimum coupling changes the story of the conflict of between the positivity bound and the kinetic screening. So here, let me summarize my talk. So we did the gravitational positivity bound and these four assumptions: unitarity, Lorentz invariance, analyticity, and Regge behavior. And in practice, we can use we can say that the regular part of the amplitude at IR must be given by a positive quantity. But the interesting point is that the negativity is allowed if we reach the scale of the quantum gravity. And actually, we get this bound. And these quantities can be computed if you suppose a UV theory. So if you suppose some UV theory, we get more concrete constraint on the bound for each UV model. That means that if we observe the negativity, we can compare this result. So if supposing some concrete model, and if this concrete model satisfies this allowed negativity, then such a UV model is not excluded. But if some model does not satisfy such a negativity, then we can exclude such a quantum gravity. So, but anyway, this is interesting, I think. So negativity is a sign of the quantum gravity. So that's all. Thank you very much.
Thank you very much for the talk. Now, if there is any question. Okay, I will ask a question myself. When you talk about the Regge behavior, of course, you always refer to string theory, and it's true. If you take string theory as your UV completion, there is explicit Regge behavior.
Right.
But what happens if the UV completion is not possibly not a string theory? I mean, how general can I assume that I will have this behavior even if I don't know what's the UV theory?
Yeah, that's a good question. And I think there are several arguments whether Regge behavior is required from some other assumptions. And I think there's some argument, so bottom-up argument, and someone says that Regge behavior is required if we suppose a causality or some other properties. But I think these arguments are not complete. And also, of course, as you said, the string is just one of the quantum gravity. But we have another quantum gravity, like Hoja-Lifshitz or non-local gravity or some other Arminius theory and so on. But typically, in that cases, the another assumptions are also violated. So in that case, we cannot directly apply this argument to other quantum gravity. But I think this is a very interesting point. So we can discuss a consequence of the another quantum gravity. And then we may derive another bound, and we can compare the observations and the consequences of the different quantum gravities.
Okay, and there is no other question. I have another small one.
I have also one when you can.
Okay. Go ahead.
Hello. Okay, let me put my camera on, although it's a bit early. Yeah. So I would like to ask, with regards, you mentioned the UV complete theory, which contains massless gravitons and Regge states.
Yes.
You said that there we can find that there is a negativity, which signal the theory of quantum gravity. Now, I want to ask, I'm not familiar with this theory. Does it have a low energy approximation, this theory?
During the low energy approximation of the superstrings. To be honest, I'm not sure. So I also think there are several arguments on the higher spin state. Because if you look at archives, sometimes we found a paper about higher spin EFTs. And typically higher spin states are predicted by string. So we may construct some EFT including the higher spin states. But
this will be the states that are invariant under rotations, 3D rotations.
Then it's not related to the present argument, because we suppose Lorentz invariance for the rotation. Invariance under
That's for the UV theory, but at low energies we break, usually in cosmology, we break time translations, but then we present
okay, I see.
Special and rotations, 3D rotations, which give rise to higher spin particles, according to some paper from Creminelli. So should be thinking about it at low energies?
Maybe related to that question, I know another paper written by Baumann. They discuss positivity in the Lorentz violating IR theory. So they are interested in the positivity on the cosmological EFTs. So they suppose the Lorentz invariance is violated at IR, but this Lorentz invariance is recovered at UV.
Yes.
And in that case, they get some bound on the some positivity bound. But actually, they say that due to the violation of Lorentz invariance, positivity is not guaranteed. But they also discuss some examples, and in these examples, positivity is satisfied. So now there are no, I think, consequences, but maybe if we maybe we can improve our argument even for such cases. So Lorentz invariance is violated at IR, And some part we cannot conclude the positivity rigorously, but this negativity may be suppressed by the violation of Lorentz invariance. And this violation can be observed by the observation, because this is IR effect. But I'm not sure, this is just a discussion.
Yes, yes, no, this is very interesting, because I was wondering how can I say from a low, if I have only the low energy theory, so the theory in the IR, so I have integrated out all these higher spin states and everything, how can I know whether this negativity is there in the, if I don't know the theory, if I do it from an effective field theory point of view?
Yeah, that's also interesting.
Thank you very much.
Thank you very much.
Okay, thank you. Is there any other short question? Okay, then
Mario,
I think we can.
can I ask something?
Is it Marco? Go ahead. Just last question before finishing.
Okay, so thanks. Thanks for the talk. And I didn't understand something because I'm not familiar with the Regge behavior. So can you explain again, and maybe in simpler terms, or to give an intuition, how the Regge behavior can save from the Froissart bound?
Okay.
Because that is because then when you consider the contour at infinity, that diverges. So,
yes. So this is a Regge behavior, and at t equals to 0, we have a graviton pole. That means that this function must be 0 at t equals to 0. And we suppose this function is negative for negative t. And our assuming bound is this quantity, this relation is satisfied for negative t. So if this function is smaller than 0 for negative t, this bound is satisfied. So
yes, but
does it answer your question?
Not because because still you have a contribution at infinity. That
infinity means
when you close the contour, so you make the contour.
No, these can be ignored. You mean contribution from these?
Yeah, the contribution that can be ignored if the field is as a gap. But for a gapless field, I don't see how you can ignore the contribution at infinity.
Okay, this is because of our assumption. So we suppose that Froissart kind of Froissart bound is satisfied even for gravitational system.
Yeah, but this is a big assumption.
Yeah, this is biggest assumption. Yes, right.
There is any hint to say that this is true? Because this is all the point of the positivity bound.
That's correct. That's correct.
With a massless spin shoe. If you have a massless spin shoe, you cannot trust anymore the Froissart bound because of the contribution at infinity.
That's correct. That's correct. But actually, this is just an example. But in string theory, this is satisfied because of Regge behavior, as I said, because we have negative j for negative t.
But for negative j, still the contribution at infinity vanishes?
No, it can be ignored because the power is less than 2 for negative t. And we are taking forward limit after all computations. So we first consider negative t region and consider leave the dispersion relation. Because we are considering negative t, we can ignore the contribution from infinity. After that, we take a forward limit.
I see. And you assume that in any case, this is the behavior when you consider even outside the string theory framework. You have this kind of here, the bottom line. So always have goes in this way. I see. Okay, thanks.
So maybe we should discuss whether this kind of behavior is necessary or not to really complete the gravity. Yes, that's correct.
No, thanks.
Sure.
Okay, so I think that's it. Well, thank you very much to everyone. And of course, thank you to Katsuki for the talk. I really liked it. And well, we'll see each other next week with the next talk, which right now, I don't know who is talking next week. Maybe Miguel knows, but sorry, I don't have the calendar in front of me. So thank you very much and bye-bye.
Thank you very much.